So think about this for a second. How does your computer, right now, talk to your server that could be thousands of miles away? I mean, how do these totally different machines, probably running different operating systems, even begin to have a conversation? Well, let's get into it, because behind what looks like a simple request is a really fascinating piece of software that makes the whole thing work. And a lot of that magic comes down to something called middleware. This diagram here shows it perfectly. Middleware is this software layer that lives between the applications you use and the operating system on the machine. It stretches across all these different computers, basically creating one big, unified platform. It lets all the separate parts of an application talk to each other without having to sweat the details of the network or what OS is running where.
All right, so here's our game plan. We're going to start with the communication challenge itself. Then we'll introduce a really powerful solution called RPC and see how it works under the hood. After that, we'll figure out how clients and servers actually find each other, look at what happens when stuff inevitably breaks, and finally, see how you can build a system that's ready for those failures.
So let's start with the big problem. If you just want two programs on two different computers to talk, why not just, send a message back and forth? Turns out it's not quite that easy. You've got a couple of options, but they all have their issues. You could use what's called raw message passing, using protocols like TCP/IP. But that's super low level. It's kind of like being handed a pile of wires and a battery and being told, go build a phone. I mean, yeah, you could, but it's going to be incredibly difficult. On the other extreme, you have things like distributed shared memory, which are way easier to use but often have a ton of overhead and get really messy when things fail. We need something in the middle.
And that perfect middle ground, that really elegant solution, is the remote procedure call, or RPC. The whole goal of RPC is to make calling a function on another machine feel exactly the same as calling a function right there in your own code.
And that's the key right here in the definition. RPC lets a program run a procedure on a remote computer, and, this is the important part, the programmer doesn't have to write any of the messy networking code. All that stuff about sending packets and handling connections, it's all hidden away.
This is the beauty of it. From a developer's point of view, you just call a function. That's it. Your program pauses, waits for the result to come back, and then keeps going. You don't know and you don't care if that function is running on the machine sitting next to you or on a server halfway across the planet. It just works. So, how does this illusion actually work? How do they pull off this magic trick? All right, let's pop the hood and take a look at the machinery inside. Now, this diagram looks a little busy, but the flow is actually pretty logical. Over on the left, you've got the caller, or the client. When it calls a remote function, it's not talking to the network. Nope, it's talking to a little piece of code called a caller stub. This stub's job is to pack up all the arguments, a process we call marshalling, and then hand that package off to the communication module to be sent across the wire. Then on the other side, the callee, or the server, its stub gets the package, unpacks it, calls the real function, and then does the whole thing in reverse to send the result back. The whole system hinges on a shared contract. It's called an interface definition. Think of it like a rulebook that describes all the functions that can be called from far away, what their names are, what arguments they need, and what kind of answer they'll give back. Both the client and the server use this exact same rulebook to automatically generate the right stub code for their side of the conversation. So let's zoom in on the client stub. When you call the function in your code, the stub just jumps into action. It builds a request message, packs in a unique ID for the function you want, and all your arguments, sends it off, and then it just waits. When the reply finally shows up, the stub unpacks the results and hands them back to your code, which has been patiently waiting this whole time. And the server-side stub, well, it's just the mirror image. It gets a packet, opens it up to see which function the client wants to run, calls that function with the arguments it was given, and then it takes the answer, packs it into a new reply packet, and sends it on its way back to the client. It's a really neat, symmetrical process. Now, this all works great for simple things like numbers, but it gets a lot trickier when you're dealing with complex data. I mean, what if you pass a pointer? A memory address on your client machine is completely meaningless on the server. So the RPC system has to be smart about it. It might have to copy all the data the pointer is pointing to, send that over, and then copy it back if it got changed. You also have to be really clear about whether your arguments are for input, output, or both. Okay, this all works great, but we're missing a pretty big piece of the puzzle. How does the client even know where the server is in the first place? This is handled by a process called binding. So first, the server has to start up and announce that it's open for business. It creates something called an export table that lists all the functions it offers. For each function, it stores a unique function ID,
or FID, the function's name, and a pointer to the actual code. Then it talks to a central service, kind of like a phone book, called the registry and says, hey, I'm over here, and here's a list of all the things I can do. So then, when a client wants to call one of those functions, it first goes to that central registry and asks, hey, who around here can do Func1 for me? The registry points it to the right server. The client then connects directly to that server, gets the specific function ID it needs, and saves all that info. Now it's locked and loaded, ready to make calls.
So far, we've been assuming the network is perfect, which it never is. In the real world, networks are messy. Packets get lost, servers crash. So let's take a look at what happens when things start to go wrong.
Here's the simplest kind of failure. The client sends out its request, but the packet just gets lost somewhere in the vastness of the internet. The server never even sees it. Meanwhile, the client is just sitting there, waiting and waiting, until eventually it just gives up and times out. And from the client's perspective, it has absolutely no idea what happened.
So the obvious solution seems to be, well, just try again, right? If you don't hear back, just resend the request. But as we're about to see, that simple idea can open up a whole new can of worms. And this diagram shows the danger perfectly. What if the first request did make it to the server, and the server did its job, ran the function, but it was the reply that got lost on the way back? The client times out, assumes something went wrong, and resends the request. The server gets this new request, has no idea it's a duplicate, and runs the function a second time.
Yeah, that's a big problem. If that function was withdraw $100 from my account, you just took out $200. If it was fire the missiles, well, you get the picture. Accidentally running things twice is one of the cardinal sins in distributed systems.
So how do we fix this? Let's check out a really clever solution that was pioneered in the Xerox RPC system. The goal is to achieve something called at most once semantics. See, when you're dealing with failures, you basically get two choices. At least once, which is what we just saw, the function might run one time, or it might run 5 times. Or you can have at most once, which is a guarantee that the function will run either exactly one time or not at all, but never, ever more than once. The holy grail is exactly once, but that's often really hard and slow to achieve. At most once is the robust, practical choice for the real world. The way Xerox RPC pulls this off is with a pretty simple but powerful idea. The server just keeps a little list in its memory called a previous calls table. And for every single request it processes, it jots down the client's IP address, a unique ID for the process, and a sequence number that the client sends along. Okay, now let's replay our lost reply scenario. The client times out and resends the request, using the same sequence number. This time, when the server gets it, the first thing it does is check that prev_calls table. It sees the entry and goes, aha, I've already done this one. So instead of running the function again, it just grabs the result it saved from the first time and sends that back instead. Problem solved. But wait, just when you think you've got it all figured out, there's another way things can fail. What if the server crashes after it runs the function, but before the client gets the reply? When that server reboots, its prev_calls table, which was just in memory, is completely gone. So if the client resends the request, the brand new server has no idea it's a duplicate and will happily run the function all over again. And here is the final, really elegant piece of the puzzle. When a server reboots, it re-registers all of its functions, but this time it generates brand new, completely unique function IDs for them. So now when that client's old delayed request finally shows up, it's asking for, say, function ID 5, but the server's new list says that function is now called ID 11. The IDs don't match, so the server just rejects the call. The duplicate execution is prevented. Genius.
And this brings us to our final and I think most interesting question. The RPC system did its job perfectly. It stopped a dangerous duplicate execution by returning an error. But now, what does the client application do with that error? Should it try to reconnect and call again? Should it just pop up a message to the user? This is the point where the responsibility shifts from the middleware back to the application developer, leaving them to figure out the logic for building a truly bulletproof system.